to our final LSTM today, Neva, who gave us some nice updates and actually got it to work really nicely. Made a PR, a pull request against our code base. Was it right here? Right here. And so we're going to walk through all of the LSTM goodness, the update that was in the tutorial right here. They're saying, here's a little exercise for you. Augment the existing LSTM part of speech tagger with character level features. Neva was able to do this and got it to work using a pooling technique. Hey, quantum. Okay. So we need to resume back on the main track here, because what we did was, once we ran into an LSTM, we're like, let's try building an LSTM, and we spent a whole week on it. All right, so we did some building models, tensor board, training, and then model understanding. So those are more of the tutorial. Every time we go through these tutorials, we always find something a little bit extra. A little bit extra. So we did this. We did the LSTM tutorial, and now we have a pretty good understanding of what's going on here. The end LSTM today. We're going to walk through all of it. Thank you for the note. Yeah, absolutely. Absolutely. Let's get into some of our code here. So what Neva wrote, so you see Neva in chat here. Neva wrote this. This is Neva wrote the LSTM updates, and we are going to review them today. We're going to go top to bottom, front to back. We're going to do that. All right, here we go. I want to close that window, and we're going to start at the very top, and we're going to walk through this entire code base. We're going to walk through it all. We wrote all this live on stream, and Neva applied some updates for this task tutorial, which we had around here somewhere. Where is that? Was it around here? Was exercise, yes. Convert the LSTM part of speech tagger with character level features. And Neva did that with a pooling using the mean of, let's get back into it here. Let's go to our code. Let's walk through the tutorial. Import Torch, import the neural network. We don't really need that. We don't. There's no point. I'm gonna get rid of this. We're just not using it. All right, clean up. Optim for our optimizer, which we also don't really need either, right? So we could just say, oh wait, we're not even using it. We're not even using it. Let's get rid of that too. All right, we just cleaned up a little bit of our code there, you guys. Cleaned up a little bit of code. You've noticed that AI is not great with what comes. We got our dictionary, we got our tags. Happy Friday, you guys. It's the weekend. But then there is HTTP3. Yeah, exactly. Now we got H3. Dictionary tags. So our dictionary is going to be our tokens. This is our tokens. Let's read this. This is our tokens. We're going to have word level tokens. We're also going to have... Wait, did we change this? We changed it. So we migrated it to letter level tokens. Level tokens, right? So that's what we merged it to. And then this is our target output tokens, which is going to be word classification. What are these two items? These are our tokenizer. These are ready for a tokenizer. So we need to build our tags and build our dictionary. And this was the word level dictionary builder. Build dictionary word level, which I believe we no longer are using, right? We're not using this, so I can just say that. So this is what's called dead code right now. You're not using this? Oh, you're not. Oh, okay. Well, that explains it. You delete, okay. So it's not using this anymore, and it's not using this. So I want to keep them, but you decided a bug. It's a bug because you can't create an output as words. Yeah, exactly, you couldn't. And labels were per word. Okay, so you fixed that. All right, I need to figure out where you did that. So you already took that into account. Your brother said hi. All right, hello, Jacob's brother. Good to have you here. Welcome on in. Happy Friday, you guys. What's up to your brother? Exactly. All right, so where'd you do this at? Vectorize. Okay, so vectorize. Normalized. Okay, I saw this. I remember seeing this here. I saw that, and so we need to walk through that. Where you put that in here, because this is new. The vectorizer is basically what took over. It took over for the features and the labels as well. Yeah. Okay. So let's take a peek here. Let's take a look. So you've got normalization here. And then you've got features, which is going to do character level features per word. Let me print out the features and see what that looks like. All right. What we're going to do next is we're going to print these out and we're going to return. So we see what we're looking at here. Python full. There we go. What do we look at? Oh, no. It's not supposed to train. Why did it return? Why did it train? Did it not save? Okay, there we go. That's what I'm looking for. Okay, here we go. So we got our features. Yes, Neva. Yes. Okay. I see it. Here's the word the right there. And the word, was it dog? The dog ate the apple. Done. That's it. That's the first sentence. Okay. So you've tokenized the letters. This makes a lot of sense. I got it now. Okay. So every letter is a token, and every one of these, what do you call them? Lists. All the essentially, this gives us the ability to assign meaning for each of our tokens. Each of our tokens has more meaning. Instead of being a one-word token, we've got an array of letters representing our token, right? So each of these arrays here is a token. Each of these lines is a token right here. So that's a token, that's another token, here's another token. And they're all represented by the tokenization of a letter. And we only have so many letters. And our letter tokenizer, let's see here, our letter tokenizer looks like this. Where is that here? Here's our letter tokenizer, right there. Using 100% of the alphabet that we have present in our data set. So I understand the dimensions now. So the thing is though, oh, this is only one sentence. Okay, so this is one sentence here. So we've got 7 words and 5 letters. There we go. It makes sense now, doesn't it? Yes, it makes sense. So you can use an embedding model to expand or contract your embedding space. I'm actually kind of curious to see how this will perform. Let's comment some stuff out here. Where are we at here? We don't need that anymore. I think we're good now. Okay, print, go. All right, let's try that. All right, so it's gonna learn. Oh, it's having a hard time learning now. It is learning though. Oh, no. Oh, it's going. Okay. Even with the smaller output embedding size, it's doing all it needs to do. So we never needed that much upper level dimensions. We didn't even need that much. So we just optimized our model, not only in performance, but accuracy and speed and training. Just by reducing our embedding. Right here. Our embedding dimensions, we reduced it. And that works for me. Me on Monday, bye. Now that we've understood that, I do want to learn how to do this. So let's take a little detour here and work on this. So we can update the LSTM model to ignore a token. So how do we do this? This is a little bit much here. I just want to say, oh, pad IDX equals 0. That's it right there. Pad IDX, where is that at here? Embedding pad IDX is this. So we put it there. Batch first, true. Oh, look at that. I could have used this. So where do we set this? So padding IDX is here. So we need to pass in, which we set to 0. So let's add that as well. It's not something that we need, it's just something that I want. Equals 0. And then we want to put that in our embedding. Drives. So we're getting the max length of our sentence, so that way we understand the dimensionality of what this is going to be. We need to know how many tokens we're going to have for every word and how big the sentence can be, right? We need max sentence length and max word length. Then we're going to go through a normalization step where we're going to split the words and lowercase them. Legacy bug. Yep, exactly. It's a feature in it's increases website time. Well, yeah, it's a feature. We want our users to stay on our website longer, right? We want them to engage more. So even if it holds them back, right? It's a feature. Don't go anywhere. We're almost done with our LSTM. It's crazy expensive, is it? Let's see if we can buy it. Let's see here. Let's see if we can buy this. It is $27. That's not too bad. That's not too bad, right? I've seen books more expensive than that. You have the PDF? Oh, nice, Boris, nice. Peter Slow. 7 minutes, more like 20 minutes. Exactly, Torva, exactly. All right, you guys, so we're gonna lock in now. We gotta lock in. I must have been thinking of something else. Hey, Peter, it's always the case. You'll buy the physical eventually. Nice, Boris. All right, let's go through this. So we build our tags, we build our tokens, which are our characters. You can see here on the screen what I'm talking about. That's what all of our features and labels are. This song's a good song. We vectorize. Vectorization is going to be converting using our dictionaries that we built, right? So we built our dictionaries right here. We got a dictionary, and let's pull this up here for a second so you can see that. Dictionary and tags are numbers, so it's a lookup. So we've got a mask that's 0, letter T is 1, H 2, E is 3. Our tags are going to be verb, determiner, and noun. We're keeping it simple. When we want to build our dictionary, that is this part right here. We take all of our training input data and we convert it into characters to encode it into a token. A token is going to be a number. Same for our output tokens, our tags, which are going to be the classifications. These are our labels, what it's going to be used to train the model on our target outputs. We vectorize, and our input data is turned into numbers. So you can see here, we've got a sentence, we've got 3 sentences, and each sentence has multiple words in it, right? So you can see here, let's see here. Let's go up here. So describing that really quick. We have 5 words, and each word can have 7 words per sentence, and each word can have 5 letters. That is the dimensions. So it's a 3D view. So we've got our batch, we've got our sentence, and then we've got our word and the letters inside of it. So that's what it looks like. Lock in, Boris. Yeah, we're locking in. Describing that. So that is vectorization. We calculate our labels, target output, our features are the input, which is the data that you see here on the right side of the screen, right over here. This is our training data, sample data. So this is why we have 3 arrays, 3 three-dimensional arrays, right? So you see, right? So you see here, this is the second sentence right here. And that is the crow fly to water, right? The crow fly to water. So you can see the first word, THE, is 1, 2, 3, easy, and so on. As you can tell, this sentence is short. So the final 2 words in our sentence are zeros. So those are 0 pads. We've updated our LSTM tagger to include that tagging for a pad value, to ignore that. We put our embedding into our LSTM. Our LSTM is going to have 2 outputs. It's going to continue to have a hidden state internally to track what it's seen previously. So that's important. The LSTM is different than all other kinds of layers. It's different than CNN. It's different than a linear layer because inside it's going to keep track of data that is seen previously, and it's going to use that data every time it gets new information. So as we pass more data into this model, it's going to use that information that it's seen previously in a hidden state inside of this layer here. And you can see what that is. So you see how we have an underscore right here? We're ignoring that underscore because we don't need to actually, if we wanted to look at it, we could. We're not going to though. And then we have a second LSTM that's going to convert from our letter to a word based. So the way Neva wrote this is to sum all of the letters into words. So our output's going to look a little bit differently, right? So print output here. A little bit, this is one sentence. This is just one sentence. So you see 1, 2, 3, 4, 5. I see 6 in there. I see 6. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, which is the length, the maximum length of our sentence. So as you can see here, we have 7 words in our sentence. That's 7 words right there. 7 words right there. Nick Gray Hill, Patience Hall, Singarg. Wait, what is this? Pearson's, O'Reilly, CRC, Taylor Francis. Many are impossible to find elsewhere. Only a handful are worth supporting. You have all of the McGray-Hill. What is that? At that point, it's 1wx because of the shape. Yes, okay. Steven, use dot shape. Okay, we'll use dot shape. Let's see. Print and print. There we go. We're going to print out the shape, you guys. We're going to print out the shape. All right, here we go. Printing out the shape. So you can see how that changed from 756. Oh, it's 6 because of our embedding dimensions. Right, okay. Because we set embedding dims. Oh, wait, our hidden dims are 6. Our hidden dims are going to be the output, which would be here. Yeah, okay. That's why it's 6, okay. So that's why we get an LSTM output of 6. 7, though, for the word, the maximum word. That makes sense. 5 for the letters. So we took the letters dimensioned and we smushed it into one dimension. That makes sense. Jinx? Yeah, the jinx there. Publishers. Oh, you guys. 7 words, 5 characters, 6 dimensions. And now you got 1 sentence, 7 words, and 6 dimensions. Hey, there we go. Yep. 7 words, 5 characters, 6 dimensions. 1 sentence, 7 words. Yep. So we are building our dictionary, building our tags, right? We're tokenizing them. And then we're going to vectorize using these dictionaries and tags. We set a fairly low learning rate. Here's our LSTM that we just walked through with a mask of 0, which is what we defined earlier. The criterion, which is our negative log likelihood loss. That's our NLL loss. Our optimizer is SGD, stochastic gradient descent, with a learning rate, standard learning rate. No momentum is defined, just a standard learning rate. We just start training the model. The easy part is the model. The hard part is the data preparation. So we're vectorizing our data. We're converting them into tensors, which Pytorch wants, right? It wants tensors. We're going to print those out for debugging purposes. We're going to train over the data set for the number of epochs that we're looking for. In this case, it's 30,000 epochs, which is more than you'd ever want. You don't typically want 30,000 epochs. Maybe like 100. That's probably something you'd be more interested in. And then for all of the data samples, which are going to be our sentences, you see right here. So we've got 3 data samples, 3 sentences. We're going to loop through and do each of these. We're going to snag out 1 sentence at a time. So this is the target labels, and this is the sentence itself, right? So your sentence and a target. Our model is going to store gradients. We need to zero those out, so that way when we pass through do a forward pass on the sentence, which is our function here that we've defined right here. This is our forward pass. Then we are going to change the shape a little bit of that output. We need to do that because our criterion, negative log likelihood loss, is expecting a very specific shape to match with our target, right? Then we backpropagate to calculate the gradients, which are going to be matrices that are going to apply parameter updates to our model layers right here. So we've got an embedding layer, LSTM layers, and a linear fully connected dense layer. When we run optim.step, it's going to use our stochastic gradient descent optimizer to apply the gradients that are calculated here. Calculate gradients for learning. The learning is going to say, when we get our delta for the criterion, this is going to calculate the loss, which is the error. How wrong is the model? Neva says this is the entropy. Entropy. There we go. The entropy. You want to reduce these. You want to make them as low as possible.